Hello. In this lecture I am going to discuss about Arndt-Eistert synthesis. This is a method to convert carboxylic acid into the next higher homolog. Okay, that is we can convert RCOH into RCH2COOH. Okay, and what the reagent we use? We use multiple reagents here. Number one, first we convert carboxylic acids into acid chloride using SOCl2. Then we treat that compound with the diazomethane CH2N2. Then the compound is treated with the moist silver oxide, okay, Ag2O. Then finally the compound is treated with the water. If you treat it with water, you will get carboxylic acid. Okay, then so what are the steps we follow here? Carboxylic acid or COOH. I'll just label this carbon, okay, and if you treat it with SOCl2, then with the diazomethane, then with silver oxide, then finally with the water, we get this compound RCH2COOH. And this isotopically labeled carbon, it remains in the acid carbon as such. Okay, it remains as such, right? And this CH2 actually comes from diazomethane. Okay, so here you are converting carboxylic acid into its next higher homolog. Clear? Now what is the mechanism, how this reaction taking place? Actually, this Arndt-Eistert synthesis involves Wolff rearrangement at one particular stage. Okay, let me show that. The first step is this carboxylic acid first reacts with SOCl2, and this mechanism is very simple, you know, so I'm not going to write that. You will get RCOCl. Okay, so we can convert carboxylic acid into acid chloride. Let me just label the carbon just for identification purpose. Okay, so this is the labeled carbon. Labeled carbon means instead of C12 carbon, we have C14 carbon here. Okay, and this is a very simple technique to understand the mechanism of the reaction, right? And what's the next step? The next step is this compound is treated with the diazomethane, and this is the structure of diazomethane, CH2 minus N2 plus. Okay, so here what will happen? Nucleophilic attack takes place, right? So that this becomes O minus. When the O minus return back, chlorine comes out as Cl minus. Okay, so let me write the product here, RCO CH2 become neutral now, N triple bond N plus, you'll get this species. Okay, then what will happen? This species, it will eliminate, see, the Cl minus act as a base, the Cl minus which is coming out here, which act as a base, that will remove this hydrogen, one of the hydrogen as H plus, because these hydrogens are highly acidic, so Cl minus will remove that, so you'll get HCl. HCl will come out and we get this carbon ion RCO CH minus N triple bond N plus. Okay, and this is a keto compound, and this is alpha carbon. Okay, it's a keto and this is alpha carbon. Now the alpha carbon has a diazo group, so this compound is often called as alpha. Let me write here alpha. We have a diazo group here, alpha diazo. Okay, alpha diazo ketone. This compound is called as alpha diazo ketone. So in Arndt-Eistert synthesis, okay, first we convert carboxylic acid into alpha diazo ketone. This alpha diazo ketone will undergo Wolff rearrangement. Okay, let me write in the next step. this will undergo Wolff rearrangement. What is that? RCO CH minus, I'll put minus with the electrons like this. This is the usual way of writing. Okay, minus means there's a lone pair. Okay, now this will undergo the Wolff rearrangement. It is called Wolff rearrangement, WOLFF rearrangement. Okay, Wolff rearrangement is nothing but the rearrangement of a diazoketone. Okay, diazoketone undergoes the Wolff rearrangement. Okay, what is actually happening here is that first this nitrogen this azo group comes out as nitrogen gas, so you'll get nitrogen gas plus you'll get a carbene, RCOCH dot, you'll get a carbene. Okay, this is called a carbene, and then this carbene undergoes rearrangement. What will happen here? This bond breaks and attacks this carbon, and this lone pair moves here, so that you will get the corresponding ketene, or CH double bond C double bond O. You will get a ketene. Okay, you will get a ketene, ketone and double bond, so it is called ketene, right? We have a alkene and we have a keto group, so this compound is called ketene. If you treat ketene with water, yes, nucleophilic attack takes place. Okay, you'll get O minus there, so you'll get R CH double bond C O minus, and here we get H2O. Right? Now we had HCl in the reaction mixture, or you can also see this oxygen become positive, so this, to neutralize this positive charge, this H plus, this hydrogen comes out as H plus and get attached with this, so you will get a enol. You will get an enol here. Okay, and this enol is highly unstable, so it will undergo tautomerization and get converted into the corresponding ketone, RCH2 single bond C double bond O OH. You will get the corresponding carboxylic acid. Okay, and if you observe the isotopically labeled carbon, let me write that. So this here carbonyl carbon is the isotopically labeled carbon. Isotopically labeled carbon. I'll keep the isotopically labeled carbon as such. Okay, wherever carbonyl is there, I'll put isotopic carbon, right? I'm sorry, here CO group goes here. Okay, so this is the isotopic labeled carbon and this is isotopic labeled carbon, right? So in the reactant, the isotopically labeled carbon, okay, present in the carboxylic acid group. Okay, carboxylic acid group has the isotopically labeled carbon. Similarly, in the final product, okay, that labeled carbon is present in the carboxylic acid group. Is this clear? So that means if you see the overall reaction, this CH2 group is just incorporated. CH2 group is just incorporated between R and the acid. Okay, yeah. So this is what we call it as Arndt-Eistert synthesis. So you can convert one carboxylic acid into the next higher homolog series. Right? Remember the mechanism. Now I'll give few examples for here. Number one, suppose if you take acetic acid or ethanoic acid, and if you treat it with SOCl2, diazomethane, then silver oxide, then fourth one water. If you use water, you will get carboxylic acid. If you use alcohol instead of water, if you use alcohol, you will get the corresponding ester. If you use primary amine, you will get the corresponding amide. Clear? Now, so we are using water here, therefore the final product is carboxylic acid. Right? Then, now listen. So what will happen? very simple. Between methyl and COH, just incorporate a CH2. CH3, CH2, COOH. You will get the next higher homolog series, right? You can also do this reaction in aromatic carboxylic acid. Take aromatic carboxylic acid and add all these reagents. Okay, you will get the next higher homolog series, that is phenyl ethanoic acid or phenyl acetic acid. SH2 group is incorporated here. Okay, you can also carry out this reaction with the heterocyclic compounds. Okay, you take this compound and add the reagents, you will get the next higher homolog series. Okay, now here I like to give one more information. This is very, very important actually. Suppose if we take a compound in which R group has some stereochemistry. Okay, say for example, I'll take this compound. COOH, then CH3, CH. Okay, let me rewrite. I'm sorry. CH3, CH2, CH, CH3. Okay, then I'll put CO, Cl. See here, I have taken a compound. This is called 2-butanoyl chloride or 2-methyl butanoyl chloride. I'm sorry, this is carbon number 1, this is carbon number 2. So in the second carbon we have methyl group. It is called 2-methyl butanoyl chloride, and this carbon is an asymmetric carbon. Okay, suppose if you take R configuration of this compound. Okay, you take compound with the R configuration, pure R, then carry out the reaction. In the final product, okay, so here I will put OH, carboxylic acid, and treat it with all the reagents. In the final product, see this, what will happen? And the CH2 group is incorporated here, so you will get CH3, CH2, CH, CH3, CH2, COOH. A CH2 group is incorporated, and this still remains as an asymmetric carbon. And if you analyze the configuration remains as such. So keep this in mind. In Arndt-Eistert synthesis, the R group, stereochemistry of the R group is retained. Okay, why? What is the reason? Because in the mechanism, right, very specifically in the Wolff rearrangement, see, in the Wolff rearrangement, the R group, this old bond is breaking here, and it is forming a new bond with another site, new site. Okay, and the same broken bond is adding here. Okay, and this rearrangement occurs simultaneously. Therefore, the R group, stereochemistry of the R group is retained. Okay, so keep this point in mind. When you in Arndt-Eistert synthesis, the stereochemistry of the R group is retained. Clear? Yeah. I stop here. We'll discuss with another set of reactions in the next class. Thank you.